Okay, let's get started. Once again, the final exam reminder over here on the screen will be in Elliott Hall of Music, Wednesday, December 16. We start at 10:30. Try to get there a little bit earlier than that so you have time to find your seat, get settled in before we start the exam. Okay, once again, try to remember where you should go. The top of the screen is the front of the hall, the stage. Okay? But if you get lost, just look for your TA or look for me. Also, you need to know your section number. And in Elliott Hall, I won't be able to project the section numbers on the overhead like I usually do. So please make sure you know your section number. All right, so today we covered quite a bit of 2014 last time, most of the top 10, 15 questions. So let's go look at 2015 today. And once again, I'm going to go in the order of popularity based on the survey. So the first one, the one at the top, is number 5. In number 5, we got this rectangular aquarium. That's 2 feet long, 1 foot deep, and 1 foot wide. Full of water. And water weight density is 62.5 pounds per cubic feet. And we're looking for the work to pump all of this thing out. Okay, so pretty standard pumping water out kind of problem. Let's make a rough sketch of what we got. All right, so this thing is 2 feet long, so that way give it 2 feet. And 1 foot deep and 1 foot wide. Right now, full of water, want to pump the whole thing out. Once again, the key equation of work is equal to force times distance. And if you integrate, then you'll get the entire tank. So you start with just one slice and then integrate after you get that one slice set up. Okay, so as usual, let's look at one slice of that water. And when you take it out, we'll see a slab that looks kind of like that. And it's 1 foot wide here, 2 feet long. And let's say the bottom of the tank is at y equal to 0. And we'll put top of the tank at y equal to 1. Okay, so give it a height. It doesn't matter where you call y equal to 0, top or the bottom of the tank. It doesn't really matter. Now in this view here, the thickness would be a small dimension in the y direction. So we'll call that dy. Now calculate the weight. Let's find the volume of this. Well, 62.5 is the density, right? And then the volume, length times the width times the height. 1, 2, dy. And that gives you the weight of any one slice of water in the tank. And now we assume that slice already got a height of y measured from the bottom. And it wants to go to the top, right? So the goal is 1, and it's already got a height of y. That's the distance it has left to travel to go to the top before being pumped out of the tank. All right, now we can do the integration. The work, we integrate that stuff, 62.5 times 2 times 1 minus y dy. And then the integration limits, we start accumulating at the bottom of the tank when y is equal to 0, and we end at the top of the tank when y is equal to 1. Right? Now the rest of this is easy. Let's take out the constant. And then integrate that. And this will be a 1/2 when you're plugging a 1. When you're plugging 0, you get nothing. So 2 times 1/2 times 62.5. And in the end, we get 62.5 foot-pounds. Okay? All right, questions? No? Okay, good. Next one, according to the survey, is number 20. Oh, this is a fun one, too. Okay, so in number 20, you're given the Maclaurin series of this thing, natural log of 1 plus x. Okay, so that's given. We would like to find the smallest number of terms of the series that one needs to add to compute natural log of 1.1 with an error less than or equal to 10 to the minus 8. How many? So, let's see. For natural log of 1.1. Here we go. So I want to calculate this thing using that Maclaurin series. But we want to know how many terms to add. So my error is no bigger. The absolute value of my error is no bigger than 10 to the minus 8. Okay. So first, let's write out a few terms of this thing, of our Maclaurin series, just to get a better feel of what they look like. This is an alternating series. and we start at n is equal to 1. And notice when n is equal to 1, we have a 1, positive 1, x over 1. And then the signs start to alternate, right? N is equal to 2, x squared over 2, and then x cubed over 3 minus x to the 4th over 4, and so on. Right? That's the series we got here. If I want to know natural log of 1.1 using this Maclaurin series, that means I let x be what? 0.1, right. So this means x is equal to 0.1 or 1 over 10. Okay, so that's 1 over 10 minus 1 over 2, 1 over 10 squared, plus 1 over 3, 1 over 10 cubed, 1 over 4, 1 over 10 to the 4th, and so on. Let's rewrite this a little bit. I'm going to rewrite it this way. I'll write 1 over 10 as 10 to the minus 1. And 1 over 10 squared is 10 to the minus 2. Right? And 1 over 10 cubed is 10 to the minus 3. And so on. Okay, so now the question is, how do we know this? How do you estimate the error when you are adding up the partial sums of an alternating series? Who remembers the error estimate? Yeah.
The error is always less than the next term.
What do you mean by the next term?
The error, like, since it's always bouncing up and down, the error is always going to be less than the amount that bounces up or down.
Okay, you got the right idea. Who wants to add a little bit more to make it more precise? If I use the first two terms to estimate my natural log of 1.1, where do you look for the error? The first one that we ignore, right? So remember this, the alternating series sum error is less than or equal to first term ignored. In other words, if I use two terms to estimate natural log of 1.1, my error is no bigger than this. If I use three terms, my error is no bigger than the absolute value of that. Right? So now look at these things here. I want 10 to the minus 8. If I use one term, my error is no bigger than 1 over 2, 10 to the minus 2. So 8 is over here, right? I want this, the part that looks like that, to be the first term I ignore. In other words, if we add up 7 terms, then the error must be less than or equal to, look at the pattern here, 1 over 8 times 10 to the minus 8, right? If we add up 6 terms, what would the error be? Look at the pattern. One term gives me that. So 1 over 7, 10 to the minus 7, right? Okay. We want the error to be smaller than this. So 6 is not enough. 6 has a bigger error than that. So we want to add 7 in order to get a smaller error. So therefore, we want to add 7. The key here is you got to remember that the error in your partial sum estimate is equal to the first of all the terms that you throw out. And once you remember that, you can find out this in a couple of different ways. But that's probably the most clear way to do it. Questions? Yeah.
Does the 1/8 here account for anything?
It just makes my error even smaller than what I want it to be. So that's a good thing. Yeah. If this is 1 over, if this is not here, then I'm still good. But the fact that in addition to being this order of magnitude, it's 1/8 of that. That's even better. But the one before that, this is too big, right? This is an order of magnitude too big. That's not good enough. We have to go at least this far to achieve that error. Questions? Yes? If it's a positive integer, what do you mean? Oh, say if this is 2, yeah, then you got to go 1 more. Absolutely. If this is bigger than 1, then we have to go 1 more. If I stop here and this turned out to be 3, then that's 3 times too big. I have to go 1 more. The next one will be something to the times 10 to the minus 9, and that will be definitely good enough. Good observation. Okay, so that's number 20. Let's look at number 22 next. 22. This is another good one. So here you're given the binomial series. Right, we'll give this stuff to you if you need that for a problem here. And we're supposed to use this to find the Maclaurin series of 1 over 1 plus x cubed. So right away, let's put that in the right form. This is 1 plus x to the power of negative 3. So we'll use that formula and let k be negative 3 to build our series. Write a few terms of these out. Let's write up to x to the 4th. We should be able to see the pattern we're supposed to see. 1 minus 3 x plus minus 3 minus 4 2 factorial. I'm going to write out the factorial. Minus 3, minus 4, minus 5. Three factorial. And we'll go 1 more. minus 3, minus 4, minus 5, minus 6. 4 factorial. 4, 3, 2, 1. X to the 4th, and so on. Okay? Now let's do a little bit of cleanup here. First of all, let's note the signs. This is positive, negative, positive, negative, positive. So in the summation we're going to put together, we're going to need a minus 1 to the n of some sort to account for the signs. And also, notice we can cancel out the 3 here with that 3. I want to leave the 2 alone, and you'll see why in a little bit. And here, we can cancel out the 4 with that 4, 3 with that 3. Again, leaving the 2 and the 1 alone. So here we got positive 3 times 4 over 2 x squared. Negative 4 times 5 over 2 x cubed. Positive 5 times 6 over 2 again. Right? And a pattern is starting to emerge here. So what do you think the next one would be? It'll be a negative. What would be in the numerator? Yeah. 3, 4, 4, 5, 5, 6, 6, 7, right? 6 times 7 over 2 x to the 5th. And so on. So we clean this up a little bit. Now we see a pattern here. Now it would be nice if the first 2 terms are also over 2, because then everything is over 2. But we can make them over 2, right? So this is really 1 times 2 over 2 minus 2 times 3 over 2 x plus 3 times 4 over 2 x squared, and the pattern is still there. And now the pattern is very clear. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, so on, so on. 2, 2, 2, 2, 2, plus, minus, and x to the n. That's n equal to 0. N is equal to 1, 2, 3, 4. Now we build the summation expression here. So what do you think it should look like? I'll give you a hint again. There's my hint. One thing at a time here. Let's take care of the alternating signs. How do we take care of that? Minus 1 to the n. Good. And let's make sure it works. When n is 0, we should have a positive 1. We do have it. When n is 1, we should have negative 1, and we have it. And then it starts alternating. All right? Next hint, denominator is always 2, so that's easy, right there. So how do you express this 1, 2, 2, 3, 3, 4, 5, 4, 5 thing in the numerator in terms of n? What do you think? Yeah, see? When n is 2, this is plus 1 plus 2. 3 plus 1 plus 2. 4 plus 1 plus 2. 1 plus 1 plus 2. Seems to work for every n. So good. And what's the last piece? X to the n. Yep. With that, we got the whole thing. Right? Minus 1 to the n gives me my alternating signs. Numerator, 1, 2, 2, 3. It's always 1 more than n times 2 more than n. Downstairs, 2 everywhere. Good. And then x to the n for the power series part. All right? Questions? Good. Okay, so that's 22. Next one on the list is number 12. This is an improper integral problem. We like to find the values of p for which that integral converges. Now remember that when you say an integral converges, that means when you actually carry out the integration, you should not get plus or minus infinity. Anything other than plus or minus infinity is good, but these are the two things you want to stay away from. First thing first, let's get infinity out of the integration limits. And as long as you remember p is a constant, then the integration of e to a constant x is something we can do. It's very easy to calculate. When you integrate e to the 2x, for example, you get e to the 2x over 2. Same thing here, e to the something x is 1 over that something, and e to the something x. And once again, remember, p is a fixed constant that we don't know what it is, but it's a fixed constant no matter what. Yeah. P minus 1, yes. Sorry. My mistake, that's a 1. And the integration limit here, we're going for x, not p. So when I evaluate this, I get 1 over p minus 1, that's some number, times e to the p minus 1 times a, minus 1 over p minus 1, e to the 0, which is a 1. Now the second part is, of course, finite. So we don't have to worry about that. We just have to worry about this. Right? So now we have to examine, we can't control a anymore. A is going to infinity. The only thing we can control is p. Remember that when you take the limit of an exponential function, and if, let's say, k here is positive, then this thing just keeps getting bigger, so it goes to infinity. But if k is negative, then it goes to 0, because we can look at it this way, right? 1 over some positive k down here, and that goes to big number. 1 over big number is 0, right? So keeping these two things in mind, this is telling us that we have to make sure the exponent of this exponential function is overall a negative. Has to be negative. A is going to positive infinity, so p minus 1 has to be negative. So therefore, what does p have to be? Less than 1. Yeah. Right? Anything less than 1 will make sure this coefficient of a is negative. And exponential to e to a negative exponential goes to 0 when the exponent gets big. So that's what we need to have happening. Okay? Yeah. Okay? If p is equal to 1, what happens to this? We got a problem, right? Yeah, so you're right. If this is not here, then p equal to 1 would be okay. But on the other hand, we're dividing that by p minus 1, so we can't allow that to happen. Okay, good. But your point is valid if these two things were not there. Other questions? Okay, let's continue. Looks like the next one is number 14. The region bounded by y is equal to x squared, y equal to 0, and x is equal to 2 has area equal to 8 over 3. And we want to find the y-coordinate of the centroid of that region. So there's my x squared. Y is equal to 0 is just the x-axis. And then x is equal to 2 is a vertical line like that. Put it right there. And then we're told that the area is simply 8 over 3. Yep, and that's an easy one to verify too. Okay, so what is the formula for y bar? How do you find the y component of the centroid? You need a moment in there. Which moment? Right, you need the x moment. The moment about the x-axis divided by, you're right, a. Yep. Okay, so imagine you divide this into little rectangles here, and then the dot there is the centroid of that rectangle. First thing we need to figure out is how far that dot is from the x-axis, because we're looking for a rotation about the x-axis. Okay, so that's always 1/2 the top curve plus the bottom curve. Distance of rectangle y bar from x-axis. And then we need the height of the bar. That's the top minus the bottom. Height, right? And then the thickness, dx. And then integration from left to right. Remember, moment is distance from the rotation axis times the mass, or technically the weight of the object. Right? So that's the distance, and this is essentially our weight here. So if we carry that out using the numbers we got, 0 to 2, of course. 1/2. Top is x squared, bottom is 0. Top minus bottom, x squared minus 0, happens to be the same thing, dx. So trivial integration. (32/10) or 16/5, right? Okay, so that gives me my mx. I have my a. So therefore, y bar is equal to 16/5 over 8/3, and that's whatever that turns out to be. That's a 5 down here to 6. There we go. Questions? For x bar here, you would do my over a, right? And my is the same idea. Distance of the rectangular center of mass from the y-axis. This part is always the same. All right, next one is number 10. Number 10, we want to calculate this thing. So this is clearly not something you can integrate by a substitution, not integration by parts, not a trig substitution either. There's no radical. That usually is not a good idea to do trig substitution without a radical. So what we got left here is a partial fraction expansion again. If you take out the x from the denominator, then the denominator is a product of two linear terms, x and x plus 1. And we know we can always do the split like that. A over x plus x, b over x plus 1. Okay, now we look at this thing here. Let's multiply both sides by x times x plus 1. Left-hand side is just a 1. Right-hand side is a times x plus 1 plus b times x. And now we balance both sides of the equation here. They have to be the same. So by inspection, right away we see a is equal to 1. And a plus b must be equal to 0. So b has to be negative 1. So now this becomes pretty easy. This turns into that, right? So integral of 1 over x minus 1 over x plus 1 both of these are trivial. Natural log of x minus natural log of x plus 1 plus some constant of integration Normally that would be good enough, but to match the answer here, we have to combine the two natural log terms. And remember, the difference of two natural logs can be turned into one log with a fraction, first over the second. So that would be the right one. Questions? Good? Good. Number 4. Oh, this is a fun one. Got some kind of solid, and the base of that solid is a triangular region. With vertices at 0, 0, 1, 0, and 1, 2. Cross-section perpendicular to the x-axis are squares. So with that information, we want to find what is the volume of that solid. All right? If I look down from the top of this object, then I see a triangle on the at the base. Vertex 0, 0, 1, 0, and 1, 2. So that's the base, right? Now, this is something that's a three-dimensional thing. It protrudes out of this picture. We can't see it on this sketch. But if I take a slice this way, top slicing all the way down, And if I take out that slice, I will see a square cross-section area. And to help you visualize this further, that rectangle we see in this view is really the bottom small rectangle, and so it's like it's a square when I take it out. All right, so it's not easy to visualize exactly what this solid looks like, but we can still find the area. So what we need to do here is to find out the area of one slice and then accumulate all of those slices by integration. Okay, so first of all, we know this is a square, so all four sides are equal. If I could find one of the dimensions, I can find the area. And therefore, the key part here is to find out how tall that rectangle is. So, how tall is that rectangle in the picture, the one that's inside the triangle? And how do you know? 2x. Why is it 2x? Right, yeah. So the top curve here, this is y is equal to 2x. And the bottom here, of course, is y equal to 0. So the height, top minus the bottom, is 2x. Right? Again, we know this is a square. So if the base here is 2x, then all four sides are 2x. And therefore, the area is 2x times 2x. And then we have a little thickness. (4x squared) times the thickness dx. That's the volume of one slice. And finally, to find the volume of this entire thing, you take the slice volume, and then you integrate from beginning to the end, 0 to 1. Right? So many of these problems you're going to encounter when you can do by slicing, like work, volume, centroid. Everything is based on the fundamental part, getting one slice right, and then let integration take care of the rest. This is pretty easy. 4/3 x cubed, 0, 1, 4/3. Okay, with that, we're out of time. Friday, we're going to finish as many of the remainder ones as we can. You can also bring any other question you want on Friday. That's it. See you Friday.